Hey guys, welcome back to the channel. Today we're gonna do Advent of Code 2015, day 7. We will not do it live as with the other days, but I go through the problem, explain the problem a bit, and show how I solved it. So basically Santa bought Bobby Tails a set of wires and bitwise logic gates. Bobby is not yet allowed to use it, and that's why we need to do it for him. If you don't know what bitwise logic gates are, so the computer stores its data as binary. So for example, that one would be decimal 7. And now what a logic gate does, it uses the bits and not the 7 and then combines bits together. So basically, if we have decimal 7, apply a NOT to it, that one will become a 0, that one will become a 0, that one will become a 0, and that 0 will become a 1. There's also AND, so AND takes 2. For example, if we have 5 and 3, we will check that both of them are 1. If both of them are 1, then the output will be 1. So in that example, only the last one is 1, so 5 and 3 combined with an AND will return into 1 or 0, 0, 1. And the one that Bobby Tails got has AND or left shift, right shift, complement, which is basically not. It's not written in here, but there's also a pass-through, so it basically just takes the input as the output. One thing we haven't touched on yet is left shift and right shift operations. What left shift and right shift basically do is they take the binary representation and then move the binary representation to the left or to the right. So if we have that example here, we just move every bit to the left, and now the 0th bit is the first bit is the second bit is the third bit, and so on. It inserts 0 at the point where we start shifting. So at 0th position, it'll be 0 now. Now what we also have is instructions on how to set it up. So we take the input, then need to calculate everything, and then check what wire A actually is. One important detail that I first missed, it's a 16-bit signal, and it's a number from 0 to 65,535. So A, it's 16-bit, and B, it's unsigned. So what you need to use is an unsigned integer of 16-bit. In Swift, that's just called uint16, so that's what we're gonna use. So if you don't use a 16-bit, what are the problems? Let's quickly show by saying it's not 16-bit but 4 bits actually. So we have 0, 0, 0, 1 for example. If we now use NOT, that would be 1, 1, 1, 0. That's 1. That's 14. If we, instead of using 4 bits, now used 8 bits, what we would have is, and if we do a NOT now, we will have 0, 1, 1, 1, 1, 1, 1, 1, which would be 254. So instead of having 14, we would now have 254. So that's why we need to make sure to actually use 16-bit and don't use 32 of 64 bits, which most languages use for integers. So those are inputs from the example, and let's quickly visualize them. So we have 1, 2, 3, and we have 4, 5, 6. 1, 2, 3 is basically X. 4, 5, 6 is Y. So we have D over here, and we have E down here. X and Y are connected with an AND to form D, and there is an OR for X and Y that will lead to E. Okay, I solved it by going from left to right. I looked at all my inputs, and then I started to calculate each step where I already got every data that I needed. And I could calculate E now because I already know X and Y. If there were, let's say, F, and F is the connection between Y and D, let's say it's also AND, that is F. At the first step, I couldn't calculate F because I don't know D. So I would first have to calculate D, and once I know D, I can then actually calculate F because now I know D and Y. And that's basically how I solved that problem. I first built up a graph, a bit like the visualization we have here. And once I had that graph, I started to solve from left to right whenever I already had the data I needed. So I would have started X and Y, and then I would have D and E. And once I have D and E, I can calculate F. And at some point there will be A, and A is actually what we're looking for. Let's say A is another AND from E and F. Then we calculate X, Y, D, E, F, and then A. And now I know A and I can stop. Okay, now let's see how I actually solved it. So I started by parsing the input first. I wrote a little function for that, parsing the input. Now what you can see in here is what I already showed before. Basically, we have inputs. Those were X and Y in our example. Those have only numbers as input and no operations or something like that. So I'll store those separately. Those are basically our entry points. We will start calculating from here. What I then do is I'll just iterate over the string, split the string by empty spaces. So basically what I have is I'll have 1, 2, 3, the arrow, and X in that example. Or if we use an OR, I'll have X, or Y, the arrow, and E. I'll just look how many items there will be after splitting. So if there's 3 items and I can cast the first item to an integer, that's an input. So for example, it's 1, 2, 3, arrow X, and I store that in the wires because those are our starting points. And if it only has 3 and I can't cast it to an integer, that's a pass-through. It says A will be D. And then there are other cases like if I have 4, it's a not. And then there are the other cases and, or, left shift, right shift. How do I actually store it? So basically, I created a type alias called operation. So operation is how do I get my first input? How do I get my second input? And then what do I do with the numbers I actually get? What does that actually mean? Let's look at some of the inputs. So basically, if we look at the AND here, it says get the input named X, get the input named Y, and output that to D. So I would store X as the first input, Y as the second input, and the operation would be taking the number from X and taking the number from Y, do a bitwise AND, and then we return the number. How do I do that in code? Well, basically I say split at index 0, which in that case would be X, and split at index 2, which would be Y. So those are our getters, and the function we use is bitwise AND. Because of bitwise AND, bitwise OR, left shift, right shift. There are some special cases. For example, the NOT only has one input, so we only use Y as an input and no other input. And what we then do is a bitwise Y. Same happens with the pass-through. And then basically we can build those operations. What I then do is I assign those to the instructions dictionary. If we look at the example again, the instruction input would be D as the key. So how do I calculate D? And then we'll have the operation take X, take Y, and then combine them with an AND. That's basically the dictionary we have here. So now that I have the input, I can now run the program with the input that I just parsed. Created a new function, run program, which takes against the dictionary string of operations and all the starting points. Started with the wires and the instructions. I go from left to right, calculate everything that I can calculate. So basically I say, well, there are still instructions left, continue. So I also added 2 small debug helpers. So keep track of count. I only print every 100th iteration just to make sure that it's still running. Get a feeling on how long it'll take. And what I also did is I take the last count of the instructions, store it, and then see whether it changed or not. Because if it didn't change, we didn't do anything. Having that in there actually led to understanding the problem a bit more, because I didn't take into account that you could also have a number as an input and not only variable names. So I didn't take the 1 into account, thus my program didn't work, and only because of that line I actually knew that I had a problem. Okay, before we continue with how to actually execute everything, let's quickly remember how our operations actually look like. So we know how to get one thing, we know how to get the other, and that will return something new. Now what we always have to do is get the value for X, get the value for Y, and then we can calculate D. And the other special case I already mentioned is we could have 1 and Y returns D. Then we don't need to look that up because we already know, we just need to check whether it's an integer or not. We need to look up Y and then we can calculate D. So the first thing, we get the first string from the operation. We then need to check, is it a number? If I can convert it to a number, it's an integer, so basically the 1 here. If I can't, I will look if I've already calculated it. So if I stored it in the wires and use that. If none of those two are the case, I'll just continue because I can't actually calculate it at the moment. So now that we have the first number, we also need to do the same for the second number. But the second is a bit differently because there are operations like NOT and pass-through that don't actually have a second input. So I first check, is there a second input? Remember, that's optional, so it can also be nil, which means that there's only one input available. If there's no second input and we have a first input, then we can actually start our calculation. We do that by taking the third argument of the instruction, which is basically our operation or the closure on what we actually need to do. We call that with our first value and 0 because there's no second value for it. And the result of that we will store back to the wires. So basically, if we have not x, we can calculate not x because we already know it's 1, 2, 3. We calculate that, store that back to h. Now h will be the result of the operation. We store it to wires. And from now on, every instruction that needs h can look up h in the wires and then basically use the value. One little detail I didn't mention yet is how we actually remove instructions. What I did is I keep track of every instruction I'm using, and then once I finish iterating over the instructions, I just clean up the instructions. You could do it in here directly. I don't like it that much because I don't like to change what I'm currently iterating over. That's why I just keep track of it and change it after it. In Swift, that's kind of safe. Usually it's not a good idea to do it. So what I do is I add to remove. In the to remove, I just keep track of the keys that we actually used. And after everything, we just remove the instructions. Okay, so now we have a value for our first argument and we know how to get the second value. What we need to do now is basically the same as above. For the second value, calculate it that time with our first value and second value. So for example, if we have the OR here, we can get X, so it's 1, 2, 3. We can get Y with 4, 5, 6. Then we can calculate the OR of it and then store it to E. Basically, we do that over and over again until we've calculated everything. There's one minor improvement we could do, knowing that we need to stop at A. We could stop once we've calculated A. I didn't do it that way. I just kept calculating until I have everything and then looked at A. Just return the wires. And that's my solution for part 1. Now part 2 actually says, take the signal you got on wire A, override wire B to that signal, and reset the other wires. If we look our input, we'll see that B is 1674 in my case. So basically B is just an input. And now what we need to do is replace 1674 with what we actually got by calculating A. What you could do is just use the number you've got from part 1 and then insert it either in the input text or replace it directly in here. I usually try to separate part 1 and part 2, so don't change anything from part 1 when I'm doing part 2, or don't change anything from the input. So what I did, I just ran the same thing as above, running it once. Then I take the original input. That's quite important. You can't just use new inputs because there might be more inputs than just one. And if that's the case, you'll remove the other inputs. That's what I did first. So basically, if we just use an empty dictionary, we would remove that instruction, and thus the program will run forever because we'll never know what C actually is. We need to use the original wires. That's why we made them mutable in here. Change B to be the value of A, and then we calculate it again. And once we've calculated it again, we just print A. And that's day 7. Okay, so that's my solution of day 7. I hope you learned something or at least had some fun. If you solved it differently or have any other improvements, leave it in the comments. I hope to see you again at day 8.